Hi everyone, we're Team Hoyas Codex, a collaborative effort between the Beck Center, the Massive Data Institute, and the Center for Emerging Technology and Security at Georgetown. We are investigating how AI chatbots and other large language models perform different tasks that support rules as code adoption for SNAP and Medicaid policies. To do this, we experimented with the policies from several states, and today we're going to focus on Oklahoma's and Georgia's policies. Our experiments use well-known AI chatbots as well as other large language models.
Thank you, Jason. Yeah, I don't think I need that. For our first experiment, I'll need it. For our first experiment, we evaluated how well can AI chatbots answer general SNAP and Medicaid eligibility questions and what factors affect their responses. Here's an example of one of the questions that we ask about eligibility, and here's the sample response of the type of response that we're looking for. After grading over 100 questions, we found that both chatbots are able to cite sources and have internet access. However, this doesn't guarantee that the data that has been trained on is actually accurate. For SNAP Georgia, only 47% of ChatGPT's responses were complete or comprehensive, and for Gemini, only 24%. Therefore, ChatGPT and Gemini are tools that are still far from being completely reliable when it comes to current information on benefit eligibility policies. For our second experiment, we evaluated how well can GPT-4o API generate accurate, complete, and logical summaries of benefit policy rules in response to different types of prompts. Here's our methodology. First, we obtain the policies, then we build a RAG environment, then we process policy data, generate the prompts, and finally evaluate the responses. Taking a closer look to our rubric, we can see we've divided by 3 categories: accuracy, completeness, and relevance, scoring from 1 to 5. Now we're going to take a closer look to the specific rubric applied to these AI-generated responses. So accuracy. For Georgia SNAP and Oklahoma Medicaid, we can see the rates are 74% and 89% respectively. And while these high scores are due to the fact that we fed the accurate documents to the LLM, we also have to recognize that there were some errors in the responses, which included data misinterpretation and focusing only on recent policies and disregarding older policies that are still applicable. For relevance, we have 58% and 53% respectively for Georgia SNAP and Oklahoma Medicaid. And some of the errors included off-topic answers or responses with irrelevant information. For completeness, which scored really low, only at 11% and 21%, due to most responses missing key details and focusing on irrelevant administrative information rather than the general eligibility that we asked for. Finally, here we can see the graph that shows the AI-generated responses for SNAP and Medicaid across these 7 question types. For Georgia SNAP, the most variance is found in what would determine if I'm eligible category. And the highest range of values are in the summary category for Medicaid Oklahoma. It is also important to notice that none of the responses made it to 15, which was the highest score.
All right. So for experiment 3, we tested 2 approaches for generating machine-readable rules for SNAP and Medicaid using LLMs. Both approaches are using a predefined, a template of predefined rules. So the first approach relied only on the LLM's internal knowledge, and in the second approach, we aim to enhance this with a retrieval augmented generation pipeline, which would add relevant policy information to the LLM's prompt. This heat map here compares the results of both approaches across different rule categories, with blue for perfect accuracy and red for 0 accuracy. We see here that the first approach had mixed results in the different categories, struggling especially with numerical and frequently changing rules, while the RAG method, on the other hand, achieved nearly perfect accuracy, except for this one category where there was no relevant information to be retrieved from the database, which highlights the fact that while RAG improves accuracy and reduces hallucinations, its success depends heavily on the availability of high-quality and comprehensive data sets. For experiment 4, we tested 3 approaches for generating software code that would determine an applicant's worker status for Georgia SNAP In the first approach, we just prompted the LLM to generate a Python script with very basic instructions provided. And given the limitations of this approach, we developed a set of detailed guidelines for the LLM on code structure and decision-making logic for the second approach. And for the third approach, we streamlined this process into multiple steps, first summarizing the policy, next creating pseudocode, and finally generating the actual code, where each of these steps was handled by a different LLM. So moving to the results of this experiment, and the first approach with the simple prompt obviously performed poorly in most of our evaluation criteria, rendering its output unusable, while the second approach, guided by detailed instructions, showed significant improvements in many of our evaluation criteria, including code correctness and logical consistency and overall output correctness. And surprisingly, the third approach with the iterative steps did worse than the second, where we observed that breaking down the task into smaller units introduced new challenges, such as losing key information between different stages, resulting in incomplete and non-functional code.
So what are our big takeaways? First, using AI chatbots to distill eligibility information has mixed results. Second, we found that large language models can generate machine-readable policy rules and policy code when provided policy documentation and when using detailed guidelines. And finally, we found that LLMs can be used to support rules as code adoption, but we recommend quantifying uncertainty, maintaining a human in the loop, and using databases with current policy information. Thank you.